Today we're going to talk about wave behavior. Our objectives are to understand that wave speed depends on the medium, understand what occurs when a wave crosses the boundary between two media that have different speeds, and then solve problems involving waves crossing boundaries and state the principle of superposition. Got a bell ringer here for you. I'd like you to work on that real quick, see once what you think. You can unpause that when you want to see the answer. So in this case, here's your canyon, and if you can imagine we're standing right here, and you yell, the sound has to hit that wall and come back. So if I hear the echo 8 seconds later, it only took 4 seconds to travel halfway in there. And it's going to take another 4 seconds to come back. So the question is, how far away is the canyon wall? Velocity is distance divided by time, or distance equals velocity times time. You need to take your speed of sound, 343 meters per second, times a time of only 4 seconds. (1372) or 1,400 meters away. So you have to be a little bit careful on these echo problems. Remember, time has to take 4 seconds to get there, and then another 4 seconds to get back. All right, wave behavior. What happens when a wave meets a boundary? Well, we can draw a wave coming towards a boundary. We get something like this, and that is called the incident wave, because it is incident upon the boundary. It's coming towards or going into the boundary. And maybe this is air on the left, and you're going into glass or into water or some other medium. But you got a boundary there. That square represents a boundary between two media. Well, what can that wave do? One thing that wave could do is be transmitted. So it could just continue on right in the new medium. This is the transmitted wave. Or what else could happen to this wave? If it's not transmitted, nice typo here, transmitted, it could be reflected. And if it's reflected, it could look like this. So the green represents the reflected wave. So the wave energy will either be transmitted into the new medium or reflected back. And the difference in the media really tells us what actually happens with this wave. So if the difference in the medium is really small, most of the energy is transmitted. Examples would be if you go from air into oxygen gas. There you have yourself a small change. Or from water into some other liquid, the difference would be small. If, however, the difference in media is large, that implies that most of the energy is reflected. So if you're going from air into water, or from air to a wall, most of that energy is going to be reflected. Now, how can it be reflected? Well, it can either be reflected upright or inverted. If the wave goes from a less dense into a more dense medium, that goes from air into water, then most of the energy is reflected, we know, and the reflected wave is going to be inverted, upside down. So if it's going from less dense into more dense, the reflected wave will be inverted. And conversely, if you're going from more dense into less dense, then it's going to be reflected upright. you can imagine, here's my medium or my boundary, and I'm going from air into water. And I send a single pulse like this to that boundary. Well, if it's going from air into water, it's going to be reflected inverted, so it's going to come back like that. If, however, we go the opposite from water into air, and the wave is like this, there's still a large difference, which implies most energy is reflected, but it's going to be reflected different. It's going to come back the same way that it left. So if we have two springs tied together, a light spring and a heavy spring, or maybe a string hooked to a dense, thick rope or something. Difference in media would be large, which would imply that most of the energy is reflected. And how is it going to be reflected? Well, it should be reflected inverted, because you're going from less dense or light to a heavy one. The wave that's transmitted is going to be at the same frequency, because the frequency comes from the source that makes the wave. So if the frequency stays the same, the transmitted wave is going to end up going slower. Therefore, you have a decreased wavelength. If your speed is increased in a new medium, then the wavelength has to be increased, because the frequency is going to be kept constant. Frequency will be kept constant because that's provided by the medium. I'm sorry, the source. My hand is making waves or something like that. And longitudinal waves behave similarly. They're just harder to show a compression wave doing that. Now let's look at superposition. The principle of superposition just says the displacement of a medium caused by two or more waves is the algebraic sum of the displacements caused by the individual waves. So the principle of superposition is what we're dealing with in terms of interference and such. So interference is simply the result of superposition of two or more waves. Just like interference in football, one guy gets in the way of another. You have two people in the same area, so they interfere. Here you have two waves in the same area, so they interfere. And you just take the algebraic sum of the individual waves. Interference can be good or bad. Usually we think of it as a bad thing, but constructive interference is simply when wave displacements are in the same direction. And this will result in a resultant wave that's greater than an individual wave's. I'll draw some examples here in a second of these things. So constructive interference, the wave displacements are going the same direction, therefore your resultant is greater than the individual. And destructive interference would be the opposite. the wave displacements are in the opposite direction, which means the resultant wave will be less than the individual waves. They're losing some of the energy. We know that particles can't be in the same place at the same time because they're matter. If you have one car and another car meets in the intersection, you have an issue. Waves, however, can be in the same place. There are tons of waves hitting us concurrently. I've got radio waves from different frequencies of stations. I've got light waves. I've got electromagnetic waves, ultraviolet waves, so they can interfere, no problem. The speed of the wave in the medium depends only on the property of the medium. We can increase the amplitude of a wave. That simply would just mean we have more energy. We can increase the frequency of a wave, make waves happen more often. That's just going to be at the expense of the wavelength. You're going to be a shorter wavelength. But they're going to travel at the same speed in a given medium. So now I'm going to show you those examples of constructive versus destructive interference. Let's imagine I've got a wave going like this, and another wave traveling like this. When they meet in the middle, what's going to happen is you're going to add up the amplitude. So if this had an amplitude of 1, as did the red one, your total amplitude when they meet will be 2. So I have to do two things. This guy is coming this way to the left, this guy coming this way to the right. After they meet, what's going to happen is the blue one will continue on this way, and the red wave will continue on this way, back with their original amount. But right here, at the time of the intersection where they meet, the energy is magnified. Conversely, if you have a blue wave, let's say we got here's my rest position. If I've got a wave traveling this way and a wave traveling this way, when they meet right here in the middle, it's going to completely cancel out because you have +1 for the blue and -1 energy for the green, so you end up with 0. After they meet, the green will continue on like that, and the blue will continue on like that. That would be complete destructive interference. You could have interference where it's not complete. Maybe something like this. This red one is up here, traveling to the right, and the green one is down here, traveling to the left. But when they meet in the middle here, what you're going to get is you have algebraic sum, 2 and -1. This is what you're going to get for energy when they meet. And then after the green one goes through, it's back to its normal one, and the red one is back to its normal one again. So that would be interference.